Hello and welcome to today's webinar. Let me just briefly introduce myself. I am Dr. Frank Richter, CEO and founder of Greenectra. I also have a position at KMUTT in Bangkok. In the past, I worked within automotive and maritime battery development. If you are an academic, you can find some of my publications, for example, in Electrochemica Acta or the Journal of Power Sources. I'm also lecture lead of the BEDXL programs, the CPD accredited battery training programs by Greenectra. In January, so very shortly, we start a new cohort of the BEDXL Pro, our flagship program focusing on operation, testing and safety of lithium-ion batteries, as well as the BEDXL Circular, focusing on manufacturing and recycling of lithium-ion batteries. If that's interesting for you, there's a link in the description of the video. But without further ado, let's talk about a very hot topic, the topic of today's webinar, the performance gap, or the difference between lab testing and the real-world performance of battery systems. Whenever we think about a performance gap, we typically look at two different things. First, there can be a gap in predicted lifetime and actual lifetime. In the past, we often considered lab testing as easier to handle for the batteries. In the lab, we often test battery aging at constant current or at least constant power. Basically, field operation with non-constant current or non-constant power was considered as somewhat more harsh conditions, and there are examples of businesses who overestimated the lifetime of their batteries based on lab data and who got into financial trouble because of that. And that's just one example of business troubles because of uneducated decisions being made. Lately, we find quite a few publications actually stating that field operation could actually make the batteries last longer than in the lab. One recent publication claimed that dynamic cycling would reduce capacity losses by 38% under some conditions. I didn't really like that article very much because it gave a wrong impression and could be interpreted in a way that dynamic cycling or field operation always improves battery life. And this is just clearly wrong. And as mentioned before, there are examples of companies getting into financial troubles because of wrong lifetime estimations. But the positive point is that dynamic cycling can improve battery lifetime compared to lab standard testing. So at the end of the day, what we learn is that real life operation matters, and it can be better or worse than in the lab. And this just highlights that we need proper battery aging testing. I wrote a comment about this publication, by the way, and I also put a link in the description of the video. So that's first. We think about the gap in predicted lifetime and actual lifetime. But there's also a gap in power losses. Of course, power missing on the terminals is related to the heat production during the operation of the batteries. And that means that power losses also have a strong relevance for thermal management and for safety of battery systems. So basically, if you want to get the same power out of your battery when it's aged, you need to run higher currents, and that means higher heat production during operation. Today we will not go into as much detail as we do in the operations module of the BEDXL Pro program, but I briefly want to show you the total heat production of a battery during operation. You can see we have three parts. The last one, that's our ohm, the ohmic resistance, times the current density squared. So this is the part of the heat production or the part of the losses that we feel most familiar with, because many of us know it from electrical engineering studies. But we also have the Tafel heat production, that's the eta times the current term in the middle, and we also have the heat effect due to the entropy change of the electrode reactions. And the important part of this equation is I marked everything in yellow that changes as the battery ages. And as we just discussed, it's not only the ohmic losses. We also have the effect from the entropy change of the electrode reactions, and we also have the Tafel heat production. And the differentiation between these effects is actually quite important, because you really need to know how to measure them when you want to model heat production during operation. And why is it that important? Well, you need to differentiate because the ohmic heat goes with the current density squared, and the other two heat effects, they grow only linearly with the current. If you look at this slide, we have all different aging processes, and the main message of this slide is that aging is complex, and aging is also path dependent. It's not just one simple aging reaction, it's many different reactions, and it depends on the operating conditions to which extent these different effects contribute to the total capacity loss and the total internal resistance increase. So in this slide, you can see many different effects. And again, we do not go into much detail, but the main message I want to tell you once again is aging is complex, aging is path dependent. And that means that you need to test aging under the actual operating conditions of your application. But that also means that aging data in typical sales brochures has no relevance at all. Maybe it's a little harsh wording to say it has like no relevance at all, but I can tell you that I have seen many test data in which different cells were tested, and the cells performing best in the lab were actually worst in the field in terms of capacity losses and internal resistance increases. And sometimes the ones that performed worst in the lab actually performed best in the real life or in the real operation. So real life operation matters. Also, when you see some aging data from some manufacturers define what is one cycle in different ways. So one of the most important questions when seeing aging data over the cycle number is the question, hey, how do you define a cycle? From my point of view, there is only one definition that should actually be valid, and I often tell people this is what a cycle should be defined as, and all other definitions are not a cycle, but not everyone sees it like that. But at the end of the day, ask your battery manufacturer or supplier how they tested batteries and how a cycle is defined. And if testing conditions are much different to your application, remember that the data may not be that relevant for you. When we come to internal resistance, direct current internal resistance, which you need for some easy models of heat production, this is also defined in different ways by the manufacturers. So here you should also be very careful and ask how they actually defined it. We know that if you want to operate a battery system for, let's say, 15 years, or you want to guarantee battery operation for 15 years, you cannot really test the battery system for 15 years. So one way to manage this is to do accelerated aging tests. So these are tests at higher temperatures. But always remember, it's not that simple to calculate back from aging at high temperature to aging at low temperature, because as you have just seen on the slide before, aging is complex. It's not just one simple process. And also be aware of the fact that if you have two batteries from exactly the same production batch, even these batteries can age differently in the field. First of all, due to some manufacturing differences. So if you get the batteries from the manufacturer, even if they are in the same batch, they don't have exactly the same capacity and exactly the same internal resistance. But production has improved a lot in the last 10 years. It's not 2015 anymore. So don't overestimate that effect. And also, there are other effects that matter. The position in the battery module matters because there can be temperature differences. The orientation matters. The framing or the pressure on the cells matters as well, just to name a few more factors. So basically, we need to test capacity losses and internal resistance increases during battery aging under the conditions the cells age in the field. And field performance can be better or it can be worse than in the lab. Basically, you need to test it. So how do we do that? How do we test like realistically, like in the field. In automotive, we use the WLTP as a typical driving profile or the typical operation of a car. In the past, we used this profile to calculate the average exhaust values of cars, but today we use it to calculate the load on a single battery in the system under real-time operation. And we can test single batteries under this load profile. But the driving profile of a customer is still different, and depending on the customer, it is more or less different from the WLTP. So the WLTP aging testing is, it's like sort of the best you can do from the automotive perspective, but it can still be quite different from the real world. And additionally, please remember again, there are still small differences in capacity and internal resistance from battery production. And as a result, we get different heat production during operation. And as mentioned before, temperature distribution in the module plays a role, as well as pressure and the orientation of the battery cells. In the end of this webinar, I want to briefly introduce the BedXL Pro with, as I mentioned in the beginning, the next cohort starting soon in January 2026. It's a CPD accredited program focusing on operation, testing and safety of lithium-ion batteries, featuring a vast amount of video lectures for online self-learn, plus quizzes and some work on real test data from the battery lab, and it also features top international experts in technical interviews, as well as online live lectures and Q&A sessions after each module with one of the top experts from the industry. Last but not least, I want to show you a really cool picture. The yellow black box you can see on this picture is actually a battery testing rig designed by one of the BedXL Pro alumni, Gabriela Bergiel from AGH in Krakow in Poland. So she works on lithium-ion batteries under stratospheric conditions. If you want to send batteries up in the air around like 30 kilometers, the test operation behavior at such harsh conditions, you need to design the test rig well. You need to understand testing, you need to understand operation, as well as when there could be safety critical behavior during operation. Most of you will most likely not work with battery systems at such critical conditions, but you need the same capabilities in terms of operation, testing and safety understanding to really design battery systems well. For example, for battery energy storage systems, which is a pretty hot topic at the moment. So if this webinar was interesting for you, please sign up for our newsletter. You can do this via the QR code, and feel free to comment as well as like our videos and subscribe to our channel. See you next time and have a great day.